it literally can cut anything. It doesn't have to be the same material. You can cut a mixture of materials at the same time. You can cut more than one thickness at the same time. It will literally, the jet doesn't care what you put in front of it, it will go through it. To give you an example of the types of things that we've cut in the past, I've got some samples here. We have some titanium. We have some aluminium. We also have some stone here. We also have some rubber. Some more aluminium here, which is a bit thicker. We have some gasket material. We have some carbon fiber. We have some fiberglass, and we can even do tube work. So, as you can see, a water jet can cut absolutely everything. Things like brittle materials such as glass, or even this stone material here, which is called Decton. It's like a man-made porcelain. This can be quite difficult to cut as well. Now, what makes it difficult, like I said before, is how brittle it is. So the real tricky part when cutting this is piercing it. The pierce, the pressure of the jet hitting that material surface can cause it to chip, crack, or in worst case scenario, just crack the entire slab, in which case then the very expensive material is complete scrap. So you obviously don't want that to happen. Now we have a very special feature on the OMAX systems which allow us to cut or pierce this material in a very particular way. It's what's called a very brittle pierce. Now, the difference of what that can do is it actually turns the pump completely off between pierces. Very brittle piercing. So the jet comes into position with the pump turned off, right? Now, normally what would happen in this situation is the on-off valve would now open when the pump is turned on, when you have pressure in the line, and you get that 50, 60,000 PSI, whatever pressure you're running with, smacks into that material surface. And it's that impact of the pressure on the material surface is what's going to cause it to chip, crack, anything like that. And that's what can cause your slab to fail. So the very brittle pierce function, what that does is that actually shuts the pump down, traverses the head into position, opens your on-off valve, your shut-off valve, and then brings the pump back on. So your pressure on the material surface is actually going from 0 up to cut pressure. All right, so you don't get that sudden impact. And it's that really makes a difference between cutting these brittle materials safely and effectively and efficiently and not cutting them at all and causing chipping and cracking and all the rest of it. Other things to be aware of as well. So when you're cutting polished materials, when you're cutting glass, things like that, materials that are going to mark easily, you're going to want to put a protective layer down in your slat bed, because what can happen is as the jet passes over that slat, it bounces back slightly and it can just mark the underside of the material. So especially if you're doing glass or polished materials, like I said, anything like that, and you want to protect that underside, just lay down a piece of core flute on your bed. Right, put that plastic, that expanded plastic stuff. You generally get it on your pallet material. It comes as a protective sheet. Hang on to that because that can be really useful to lay down on the bed, and it just protects that backside of the material from the bounce back over the slats. Okay. When you're cutting laminated materials, now again we have an issue with piercing laminated materials. What happens is in the split second before the jet passes all the way through and out the back, it looks for the path of least resistance out. And that path of least resistance out is into the material, it's in between the layers. So it causes pretty bad delamination when you pop materials apart. There's only really one truly effective way of piercing material like that, safely, reliably, 100% of the time, and that's to pre-drill your start point. Now, we do have a drill option, which is all automated into the system, where it comes over and it drills all the start points like that, and then it brings the jet in and it starts and does its cutting. You can also hand drill your start points as well, if that's an option, or you can start your jet off the plate, bring it on, and cut away. So that's really, like I said, laminated materials. Some laminated materials you'll get away with it, where you can just do what's called a low pressure pierce, or you can even do the very brittle pierce function, and that will still manage to get through it, but it can be a little hit and miss. So like I said, the only way to do it 100% reliably is to pre-drill your start points, okay? With the OMAX software, what you can also do is you can recompile your tool path with just a single click to just pierces. So you can then use your nozzle to locate the pierce points throughout the blade, throughout the sheet, sorry, and then mark them and pre-drill them before you then come through with the jet. So again, there's another effective way of quickly and easily getting your material to pierce effectively and reliably. Okay, next question. Thicknesses. Let's look at thicknesses. So one of the issues that we find when cutting thicker materials is maintaining the detail in the corners and the tight turns and all that kind of stuff. I don't know how much everybody out there knows how the jet behaves. So what we're going to do is I'm going to show you a little feature here on our computer, which shows you how a waterjet behaves when it's cutting materials. And that will hopefully help you understand why cutting thicker materials has, you know, a high degree of, what's the word I'm looking for? High degree of control required to make sure that it's correct. So as you can see here, we've just got a piece of material with a simulated jet on it, which is moving quite slowly at the moment. Now, as I speed that jet up, you'll be able to see how it drags backwards. Okay. Now this is pretty much going just a kind of a flat out. That's how it behaves. And if I come around to the side, you can also see how the jet's bouncing side to side. Now, imagine that drag back going round that sharp corner that just happened there. All right. What's going to happen is that drag on that jet is going to stay there. So you're going to end up with a big flare down the bottom of your cut. So what OMAX have done over the years, they've refined this, they've tweaked it, and they've just about got it perfect now, is all to do with how the jet behaves when going around the geometry of a part. So tight turns, small radiuses, straight lines, large curves, all that kind of stuff. It behaves differently for different features. So if we come back to the screen again, John, I'll show you what happens. So as you can see, the jet's approaching the corner. And what happens is, when it gets within a certain distance of the corner, it will then start to slow down. It will slow down, slow down, slow down like that. So you get a pretty straight jet. Then once it passes the corner, it will then start to accelerate again. So what that does is that allows the jet to come straight. So you get that tight control of the jet before you turn that sharp corner to make sure you actually get that sharp corner that you're after and not a big flare out at the bottom. And it's how the OMAX software controls that on thick materials that gives you a real point of difference. So to show you what I mean, this is a big 100mm thick piece of titanium. And you can see here, all the way down to the bottom of the cut, how straight that is all the way through. And that is done by just controlling the feed rate, nothing else. And so we've got a piece of aluminium here. Same principle. 100mm thick piece of aluminium. And by controlling that feed rate, you can control how it behaves around the features and make sure that you get the right feature all the way through the thickness and you don't get that big drag. So what that does is that allows you to control the taper. Okay, now another question we get asked is about taper. So how do you control taper, right? With a waterjet system, unless you actually physically tilt the head over, you're never going to get rid of taper. Okay, so in terms of accuracy on your thicknesses, you have to take your taper into account. On 25mm thick, up to about 25mm thick, you're going to achieve about 0.1 of a mil of taper at best. You can go a little bit more if you go faster. You won't get it much less than that. Then up to about 100mm, you could go up to about 0.2, and then above 100mm thick, obviously then the taper gets more and more, but you'll never really go more than about half a mil up to about 200mm thick on material. Okay, so the thicker you go, the harder it is to control taper, obviously, because the bottom end of that jet is so far away from the top. All right. Okay, so I think that we're going to keep this pretty short and sweet, guys. Keep them down to about 10-15 minutes. So I think that's pretty much it for today.